This is week, I think 10. Next will be week 11. So some of the to-dos you will see. This week is, of course, the PAs and the quizzes are doing. And exam number 2 is coming up next week and next Wednesday. It's only just a little bit more than a week from now. All right. And some of you might have visited the exam 2 channel and see also that what is the scope of the exam. So it will be PA 4 to 7 from chapter 2.6 to cover the entire chapter 3. Okay. And there'll be also some difference between exam 1 and exam 2. So make sure you read these, and link for the Google form and Google Me for the exam. The placeholders are here. Okay. So they'll be ready at the day of the exam. Similarly, the accounts for the exams, they will be activated again a day before the exam. So everything else will be the same as exam 1 except for this. Okay, bullet number 4. All right, so, okay, hi Angel. Good. So, last week we spent a lot of time talking about the RDTs, the Reliable Data Transfer Mechanism in TCP. Okay, so you see that in TCP, it's a working mechanism, so that you see that all those components in the general RDTs are made a lot more concrete. For example, how do you estimate the timeout interval? And how do you count the data? Okay, so in TCP, it's not counting packets because you have packets large and small, right? If you count the packets, well, that sometimes, right, can limit the amount of data you can send. Okay, so counting bytes agree better with the measured available bandwidth. Okay, and it's a more common, measurable metric for all connections around the world. Okay, you also hear the entire RDT mechanism in TCP, and you should see now that TCP's RDT is very much like go back in, but with the receiver and also caching packets. So it's kind of go back in with something that's a little bit more like the selective repeat, which is at the receiver end, you also need to allocate memory. Okay. And there are some optimizations TCP does, for example, fast retransmit, delay ACK, and all these. Now, delay ACK, I'm not quite sure whether operating systems have turned the delay ACK on. But I know for sure that fast retransmit is a optimization that oftentimes the operating system take this option on. So most of the TCP connections we're sending data with do have the fast retransmission optimization working, which is what? 3 duplicate ACKs quickly retransmit. All right, and we just have 2 more videos to watch about TCPs, and particularly about the connection we need to establish to do the reliable data transfer. So the first video is called Flow Management. Okay, later today we'll start talking about congestion control, but this flow management thing is actually to control a flow from the sender to receiver, so it's end-to-end. Congestion control is to try to do control from what we sense happening in the network. So it's somewhat different. So let's check this first video out. How does TCP do flow control, and what does flow control mean?
And that takes us to the flow control of TCP. Allow me to explain. So this is again the protocol stack. This is the application layer, transport layer, and the network layer. And packet is coming in from below like this. So network layer is going to pass the segment to the TCP receiver right here. If everything is okay, TCP receiver is going to extract data and pass it further up. What's going on really in the implementation in the operating system is this. that data does not go directly to the application layer process. There's this place here called the receiver buffer. So the packet being extracted is actually temporarily stored here, okay, waiting for the application layer process to fetch it. So the application layer process is going to remove data from the receiver buffer. Just like the TCP receiver here is going to push more data into the receiver buffer. And TCP flow control is needed when the application is drawing data slower than TCP receiver there, delivering data up. Because when that is the case, the buffer space will be what? Occupied. More and more and more and more, because outgoing slow, incoming fast. And eventually the space is going to be exhausted. The subsequent data will be dropped right there between TCP receiver and the receiver buffer. And this is super bad because TCP here is working very hard to try to get this packet in. So full control there is this. For the receiver to tell the data sender, slow down a little bit so that you will not be overflowing the receiver buffer by transmitting too fast, too much. And the way flow control works is this. It works by tracking this variable, RWND. In the operating system, there's this receive buffer. This is well defined, and it's actually the size of the receive buffer space. Now, initially, RWND is going to equal the receiver buffer. Whenever TCP receiver sends data to the upper layer, this RWND is going to be subtracted by the amount of bytes being passed up here. Whenever the application layer process is drawing data out of the buffer, the RWND is going to be incremented by the number of bytes there. So RWND is essentially tracking this, the free buffer space. So once we manage to track the free buffer space, TCP receiver here will advertise the free buffer space by including RWND in the receive window field in the packet header, in the TCP packet header, and send it back to the sender. And that's when sender knows it needs to limit its sending window so that it's smaller than RWND. So you see here at the sender side, the sending window not only is limited by the congestion control mechanism, but also by flow control mechanisms, RWND. And that guarantees the receiver buffer not being overflowed. So receive buffer here, in most of operating systems, when you create a socket, it's set default to 4096. But most of the modern operating systems these days would actually give you different receive buffer space by default. If there's more space, then this is potentially higher.
All right, so that was flow control. Quite easy. So essentially tracking how much memory is left on the receiver side buffer and send that amount back to the sender. So the sender will limit the sending window, so not to send more than the amount of data that the receiver buffer can hold anymore. Next, let's hear out how does TCP establish a connection and tear down the connection. So this is actually the thing that TCP needs to do before data transmission can start, before RDT can start, before flow management can start. Okay, so connection establishment, and everything after all the data are done, being transmitted, tear down of the connection.
Last is the connection management of TCP. There are two parts. First is establishing connection. Second, breaking a connection. Let's talk about the process of establishing connection. It needs to be done before exchanging data, and the process is called a three-way handshake. Okay? At the end of the process of three-way handshake, we would establish a connection, or aka a socket. So once the socket is established, two ends can begin sending data to each other. So the socket establishment process is also exchanging some number of parameters. Now this is crucial because later on, when the client over here on the left is trying to send data, in the packet header there, it needs to carry a sequence number. When that packet arrives at the receiver, which is the server is going to examine the sequence number in the packet header to decide whether to extract the data out and pass it up to the application layer. And when do we extract the data? only when the sequence number equals the expected sequence number. So there is a certain parameter at the receiving part, okay, that needs to be initialized. Okay? And because either side can be sending data, receiving data. So server here would also need to tell the client what is the initial sequence number server will be using. Therefore, the client can set the expected seq num accordingly. And this illustrates the three-way handshake. Client, server, both initially just listening, and client at some point wanting to request some data will then initiate connection, dial into the server. Okay. So it's gonna choose initial sequence number to tell the receiving of the request messages. And it's gonna be sending a TCP sync packet or sync message. Now, if you recall back in TCP packet format, in the header part of it, there are a number of these flags, one can set. So sync packet is the packet with the sync flag being set, the S flag being set. That is also called the sync bit. So that bit is going to be turned to 1, and the initial sequence number is going to be in the packet somewhere, and that packet is going to arrive at the receiver, which is the server. So client, after sending the data, is going to be in the sync packet already sent state. Now the server will then in the sync receive state. So server here will be doing two things. First, send back an ACK, right, to tell the sender of the sync packet that the sync packet is received. Okay, so sync ACK is such a packet. That is to ACK receiving the sync packet. Right? The server here will be doing yet another thing. Choosing its own initial sequence number, and let's say it's Y, and this Y will be stored somewhere in the sync ACK packet as well. So you see here, this packet goes back, and the sync ACK packet is going to have the sync bit on as well as the ACK bit on. And in sequence number, server tells the client it's going to start from Y. Okay. And this being an ACK packet is going to tell the sender of the sync packet that, hey, the next one I'm expecting is x plus 1. All right, so next seq num is already set to x plus 1. And lastly, when the client receives the sync ACK back, so it's going to receive the sync ACK. At this point, the client is sure that the connection is established. Okay? And so server is live. The last thing the client needs to do is just to acknowledge receiving the sync ACK. Okay? So it's just an ACK packet, and the ACK number is Y plus 1. Because this guy here observing the initial sequence number of the server is Y, then therefore the next seq num is set to Y plus 1. And that number is also shown in the ACK sequence number. And so server finally receiving the ACK is sure that the client is live and the socket is now complete and in the establishment state. The closing process is actually not exactly three-way. It's actually independent. The client can initiate the closing process. The server can also initiate the closing process. And the message exchange is just a pair of fin and ACK. So a fin packet out from the one who wants to close. And ACK will come back from the one receiving fin. Right? So there could be simultaneous fin exchange between the client and the server. So the client and the server are both exchanging data. And finally, the client here says, okay, I've finished sending all my data requests, so I'm ready to close. Okay. Then it's going to enter the no longer send but can receive data state. That is called the send fin, and now wait for the rest of the data to come in. So you see here, the fin packet is the packet with the fin bit on. Okay. Server here receiving the fin packet sends back an ACK. So ACK bit on, and then ACKing the sequence number. Server here will enter the close wait. So server knows now that the client wants to close, but it's not quite yet closable because client setting close is just that finishing sending request. There could be some more data waiting to be sent here. Okay, some more ACKs waiting to come back here. Okay, so server needs to finish all these other data that's remaining. But client here receiving the ACK for the fin. It's pretty much done, and just waiting for the server to say everything is already sent, so you're okay. So finally, server says, done with all the data. Okay, so sending fin. Client here is receiving the fin, sends back the egg. Okay, saying good, that's close. Server can now close safely, no problem. But client here needs to wait 2 maximum segment lifetime before it can really close. And this maximum segment lifetime is usually 60 seconds long. Can you guess why? Why the client needs to stay so long until it can really close the connection?
Why? Okay. Those who figure out why and provide an answer in the Ask Us Anything get extra credit. Okay. So that with that we conclude TCP's reliable data transfer. We now enter another major topic. So far in chapter 3, all that much we've talked about are just to do reliable data transfer, having no loss. There's a major task we are yet to do, which is to do congestion control. Okay, so if you think about it, sending packets, sending data over the internet is much like having cars traveling the transportation network. When we push data too fast, too fast, into the network, the network gets congested. Okay, and it's not good to have congestions all the time. Okay, so congestion control is a major topic. It's something that we are hoping to implement such that the internet can go smoothly, okay, and satisfying the demands of the user. So that's here out the overview of congestion control.
Principles of congestion control. Now the section title sounded a bit like we're going to talk about these general mechanisms to do congestion control. Well, but no, in 3.6, what we're going to talk about mainly are what's causing the congestions to occur. What is so bad about having these congestions? So hopefully from the discussion you see a little bit the nature of congestion and the design elements of doing congestion control. Congestion is this thing, having too many sources sending too much data too fast into the network. And by network here, I actually meant the core of the internet. So congestion here sounds a little bit also like the problem we see in TCP, such that we need flow control. The situation there is that the TCP source sending too much data too fast into the receiver buffer. So the congestion there occurs at the receiver. And the resources that's being exhausted is the receiver's buffer space. Now when we're talking about network congestion, congestion is occurring here, routers. And these are the machines that are in the core of the internet. And the resources that we are exhausting there with congestion occurring are these, the buffer space. So router buffer is the resource that we're trying to handle. Now when we are all sending data into the core of the internet, you see that these buffer space can quickly be exhausted. If not, hey, we will have to wait a long time, or these packets will have to wait a long time, right, until they get served. So what's bad about having congestion is this. We see packet loss when the buffer overflows, or long delays when there are lots of packets waiting there to be served. Congestion there is one of the top problems in computer networks, just like reliable data transfer, and probably a little bit more serious than reliable data transfer these days. Coming ahead is a series of these scenarios, growingly more general, and hopefully by the end of the discussion, you see congestion is something that's really bad. You could invest a lot of time, a lot of resource, but you ended up having nothing.
All right, let's go over the scenarios. There are 3 of them.
Scenario 1 is this. Okay, you see here, we have 2 senders, host A and host B, 2 receivers. Okay, so 2 servers receiving requests, I suppose. So 2 senders, 2 receivers. And we do have a link in the middle. The capacity is what? R. There's a router on the link and carries infinite amount of buffer space. Cool. So what that means is that there are no packet drops, because it just takes a long time for the packet to go, but they're never dropped because we have infinite amount of buffers. Now let's assume that there's no bit error, therefore there's no need of retransmission because there's no packet drop and no bit error. Okay. Now let's use lambda here to denote the rate host A and host B are injecting data into the network. Okay, so host A and host B are actually raising the rate, okay, as time goes. Let's use lambda out to denote the amount of data that arrives at the receiver. Now, when lambda in is really low, starting from here, when we increase lambda in, the more data we send in here, the more data comes out here. Okay, so lambda out will actually increase accordingly. But this will only go up to here. When we exceed the link capacity, because there are two flows and link capacity is R, so each flow gets only half of R at best. That means lambda out here can only, at best, being R divided by 2. So even though lambda in continues to send more, but no, we hit the limit, hit the ceiling here because resource is limited right here. Okay, we don't get to push more out. So increase sending rate, receiving rate accordingly. But here, even though we're increasing the sending rate, but the receiving rate remains the same. Now, the delay is going to show this way because when lambda in continue to increase, as you reach half of R, it reaches also the link capacity, right? Because this is also half of R, this is also half of R. And so at here, it's R completely occupied. So when we approach the link capacity, the queuing delay is what? Approaching infinity. So the first bad thing you see already, long delay, when we send a lot more data and more than what the network can accommodate.
And that was a scenario with the assumption that we have infinite amount of buffer, which is not real, right? Do you have infinite amount of memory on your computer? No, memories are quite expensive. So let's check out the second scenario that is a little bit closer to reality.
And scenario 2 is actually very much like scenario 1. The only difference is this. The buffer space in the router there in the middle now has only finite amount of space. So in scenario 1, we have infinite buffer, so we don't have packet drops. Right? So what's bad about that scenario is just we will have long delay. But now in scenario 2, we have finite buffer space, so potentially we could have packet drops. So potentially we need to retransmit packet. And retransmission here is at the TCP layer. So if lambda in is what the application layer processes generating the data to send out to the network, that lambda in prime denote the amount of data the transport layer needs to send into the network in order to complete the job. Okay? Then we'll see lambda in prime should be greater or equal to lambda in because it should definitely contain the amount of data we need to send out and plus potentially retransmissions of some of these data. Right? Lambda in, lambda out, the same thing. At the application layer, lambda in is going to be very much like lambda out. How much we send out, in the end, at the end of the time, lambda out is going to come out. And that was just to describe scenario 2. Now, let's assume the sender knows perfectly well when the router buffer is available. Okay, so sender sends data out only when there's buffer available here. So no packet drop. Okay, the scenario goes like this. At the transport layer, now we keep a copy of the data just in case we need to retransmit. But the packet will arrive at the router because there's free buffer space, so it travels through the network, reaching the destination. Okay? And that goes back and we remove the copy. Right? So this is when the sender has perfect knowledge of the routers in the middle of the internet. Now in this case, there's no need of retransmission either, so lambda in prime is essentially the same as lambda in, and lambda in is essentially lambda out. So you see the same curve. We could have lambda in increasing, and we get the same lambda out up to the capacity of the link. To be more realistic, let's assume sender does not know whether the buffer space in the middle here is going to be free or full. Okay. So we'll have packet loss this case, because when the packet arrives at the full buffer, it's going to be dropped. And in that case, they will have to resend the packet. So packet arriving at the transport layer, at the sender side of transport layer, we keep a copy. Now, that packet arriving at the router sees buffer full, so drop the copy. and the sender there waits for some amount of time and retransmit. And this time, it happens to be free and it passed through. Receiver there receiving the packet sends back acknowledgement and removing the copy of packet here. And you see, in the application layer, there's only one packet being sent. But in the transport layer, we send 2 times the same copy. So lambda in prime, the output rate at the transport layer, it's definitely going to be higher than the output rate at the application layer. Now the output rate at the application layer for TCP is going to give you the same thing at the receiver end. Therefore, you see lambda in prime versus lambda out. It's going to be lambda in prime higher than lambda out. So in the end, even though the lambda in reaches its capacity, half of R, okay, but we don't get exactly half of R out here because some of these half of R is going to be used for retransmission. So this margin here, unfortunately, is used for retransmission. So the actual amount of data coming out, less than half of R. And you see here, the bad thing, number 2, we have retransmissions when there is congestion here. To make it even more realistic, we know earlier when the buffer is full, the packet can be lost. The thing is that at the sender side, in order to detect if there's a buffer full, if there's a packet loss, we set up timer as well. Okay, so these timer can go out prematurely and therefore sending copies while we don't really need it. So it's illustrated by the animation here. Data coming from the application layer process, we keep a copy at the transport layer sender just in case we need to retransmit. Now let's assume that the buffer is free, but in case the timer is too short, we time out prematurely. We ended up sending 2 copies of data here, okay? While only one copy of it will be arriving at the application layer. So lambda out remained the same as lambda in, but we see here, the lambda in prime, this is going to be higher than the lambda in prime in the previous assumption, where we do not assume the timer can go out prematurely. So the performance of lambda out here as lambda in prime increases is going to go slightly worse. The margin here is going to be bigger because what? Lambda in prime here, we need to take into account the retransmissions. Now we also need to take into account the duplicates that are not really necessary. So we see delay being bad, retransmission being bad, and what's even worse is that we could have unnecessary retransmission. Now if you think about it, congestion, we see that having packet loss, having delay, not good. But to address packet delay issue, to address packet loss issue, we need a retransmission mechanism, the RDTs. As a result, what? We are actually generating more traffic into an already congested network. So the cost, okay, of congestion is actually not that trivial. Okay? It's not just that the delay rises, it's not just the loss increases, but also the traffic being dumped, injected into the internet also increases. So in the end, the internet is doing even more work, while the throughput is not getting better and sometimes even worse. As you see, the margin here is bigger than the previous case.
All right, so last scenario, this is even more realistic because the internet is a network of computers interconnected to each other. So the path is usually not just one router, but multiple routers.
If you think scenario 2 is bad already, where we do more work, right? Lambda in prime increasing, but lambda out increases at the beginning but saturates toward the end, okay? So beyond certain point, the more work you do, you don't get more results. But here, I'm going to show you an example. Yeah, at the beginning, the more work you do, the more results we get. But in this scenario, the more work you do, you might end up having less results. And the even more work you do, the even less results. And here's the scenario. We do have 4 senders now, or 4 hosts, A, B, C, D. And each of them is generating a flow traveling multiple hops. So this is one hop. This is the second hop for the red flow. So multiple hops. And yeah, we might run into buffer full situation, therefore we could have packet drops. And therefore we do need a transport layer mechanism to try to do retransmission. So similarly, we have the lambda in, which is the input rate from the application layer. And lambda in prime being the input rate of traffic into the network from the transport layer. Now let's focus on the red flow coming from host A. and the blue flow coming from host D. Okay. And these flows will increase the sending rate lambda in. And therefore, lambda in prime will also be increasing and sometimes increasing faster than lambda in. Now, what's going to happen when lambda in and lambda in prime increases? Now, at the beginning, you see the red flow, the red packets coming into this router here. Okay? And as the rate increases, the buffer space here is going to be occupied by the red packet, just like the blue packet in the meantime, coming into the first hop router and occupying the front sections of the buffer space in the router there. Now, after a while, the red packet is going to come out and enter the second hop. Just like that, blue packet is going to come out and enter this router here at the top. And the blue packet will be coming in to compete with the red packet that is already occupying most of the buffer space. Okay, so this is already pretty full when the blue packet just arrived. Okay. And as the lambda in increases as well, as they both approach a half of R, you see this. The buffer space is going to be very full and quickly. Red packet will be dropped, but blue packet will be dropped even more because very few of these blue packets get into the queue and have a chance to go out, finally reaching B. So as lambda in prime increases, the arriving blue packets at the upper queue here, most of them get dropped, and therefore the throughput very small. So you see right there in scenario 3, the blue flow, right, when lambda in or lambda in prime is small, right, when the network is not saturated, when the buffer does not overflow, then the more work we do, the more output we get. But as it approaches half of R, we see blue flows, blue packets gets dropped a lot. So originally, not so bad, but in the end, when buffer flow could occur here, blue packet gets very little chance of coming through, and the throughput is going to be even lower, than when the lambda in here is small, really bad. So that is another cause of the congestion. Because what? The bandwidth that is transmitting these packets when they're traveling upstream, it's all wasted. The amount of waste is actually not quite comparable to retransmission or unnecessary retransmission. Those are probably very small. Therefore, in the lambda in and lambda out plot we saw earlier, the margin is very small. But here, the upstream bandwidth, those are all wasted. So the amount of resources we are wasting here could be very high. So the hidden cost here, waste of all these upstream bandwidth resource, and this is a big cost. So message here, congestion, really, really bad. But what can we do about it?
Okay, what can we do about congestion? Well, let's try to see if we can learn from how car traffics, vehicular traffics are being controlled. So quiz 25 here is asking, pretend that you are an Uber driver, and you are serving the line between the city center to the nearby airport. So for those domestic students, consider you're driving all the time from Taipei to the Taipei airport or back. The thing is this, this is a busy route usually. So on highway number 1, from city center to the airport, very often you get congested. And today you took on a customer and then you're driving to the airport as well. And you see right now it's badly congested. So Q1, ask you, can you come up with a couple reasons, to see why why you see traffic congestion? So what are the reasons that you run into congestions? Why you have congestions? So that's Q1. Q2, when you see congestion, it's not good, right? How do you inform your friends or your colleagues who are also Uber drivers to try to avoid congestion here? So what's very interesting about congestion is this. It come and go also, right? During rush hour, you have congestion. But when it's off-peak hours, then not many cars around. So congestions can come and go, and congestion can also happen at one place versus another. Okay, but why there are congestions? So Q1 asks you so. Q2, if you are driving and you see a congestion, how are you gonna tell the other guys to not come on the highway, right? Because it's already congested. All your friends and colleagues will do will be just like you, get stuck and waiting. So let's go to the Slack, and I think you'll be able to find the channel W10 Week 10 Quiz 25. Okay, so Quiz 25 is posted there as well. This definitely try to find your teammate and have a discussion. Okay, so what do you think are the main reasons causing traffic congestion? Q2, if you are a Uber driver, how are you going to tell your friends so that they can avoid coming into congestion? All right, so how about taking some 10 minutes, right, to think about this? Oh, okay. Some team is actually very fast. Okay, so maybe we just take 5 minutes here, okay? Because it's almost like an everyday problem. You guys all have probably some experience with this. Hey, don't tell me that ask your friends to tell their customers to take the metro line to the airport. Okay. Let's see. Let's go to the Slack space directly because I already see some teams typing things up. So Team 5 from Jia Hong. Reasons for congestion. Bad weather, of course. Yeah, this is actually one of the major reasons. When it's rainy, you want to slow down a little bit because the visibility is not quite as good as the usual weather. Of course, too many cars. And yeah, I think a major reason is also having accidents or having some constructions. So Q2, for Q2, you say you send a message to the fellow Uber drivers by phone. Yeah, because you're probably stuck and not being able to move, right? So what you can do is probably ask, if it's iPhone, right? Hey Siri, send a message to someone, and with a short text saying congestion going on right now. All right. Oh, I see. Okay. Let's see. Team 4 from Jason. Okay. Holiday. Yeah, holiday is also a major reason. Or to see a lot of traffic to the airport, it's usually the time that we have quite a few planned scheduled to depart. Yeah. So many people want to travel, okay, and needing to go to the airport at the same time. Second, accident, definitely. Okay, so very interesting. Very interesting reason, unique reason. And you tell the other drivers by calling them. Oh, and in the meantime, you suggest an alternative route. Okay, that's really nice of you, right? So you specify that there's a congestion on highway number 1. Okay, and as you are driving here, you probably see that the earlier segments are fine, but it might be better that they take the earlier segment on highway 1, but exit at a certain exit and and take the surface street, okay, from a certain exit and on. Okay. Team 15. All right. While there are too many vehicles or there is a car accident, yeah, so these will all cause congestion, right? And just like bus, we can tell our friends that they can choose other routes, or if there's a radio or website. Okay, interesting. So of course you could call or text your friends, but you could also use this, a radio station, uh, and maybe some website or some sort of apps that you can share information about traffic condition. I guess so. Um, I think one can actually look up Google Map and see also how traffic condition is like at a certain point. Okay, using other forms, other than the phone network, you use a FM network or you use internet, okay, to tell other people that there's condition. And team 2, rush hour, rainy days, definitely. Wireless intercom, yeah. So I think those will be the radios. Okay, not necessarily the FM radio, but the direct radios. Okay, the walkie-talkie type of radios. Okay, interesting. Too many cars, car accidents, some drivers too slow. Oh, I hated that as well. Okay, yeah. So hey, every now and then we have new drivers coming on the highway, coming on the street. They'll be very, very cautious, and sometimes they are not aware that they are driving too slow. Yeah, very interesting. Yeah, some drivers driving overly cautious, right? Very good point. Send a message or use the radio to tell them. Car accident. I see that the answers are converging to all these types, and as a driver, as you are stuck, then you call directly as you are experiencing the condition. Okay. Well, what if there's a regulation saying that, hey, drivers in car can never touch any other electronics or look down on your phone screens. Okay, you have to have the eyes maintained on the streets all the time. What would you do then? Would you inform your fellow drivers right there in the middle of a condition, or you wait until you can stop somewhere and then inform your fellow drivers for the condition? Let's see. Yeah, so this is again, Jimmy is suggesting going to a website, right? Either you report condition or you can check how bad the condition is, right? All right, I think that's about it. Okay, so think about the case that you cannot really be holding any electronics or looking into any screens while you are driving. Okay, because even though you run into conditions, but it could be slow traffic. In a slow traffic, looking into your phone screen is also very dangerous. Okay. Okay, so I think Yo is typing up something as well. Rush hour, car accident. Okay, informing the president of the fleet, of course. Okay, or just give up because there are not many other ways around from the city center to the airport. Oh, okay. So maybe the remedy here is that to write to the mayor that we need another highway, right? And let's see, slow cars. Okay, yeah, like Howard, right? You probably don't like that either. Taxing group or Uber drivers. Yeah, so line your other Uber drivers, of course. Okay. Yeah, I think you got it. Having traffics on streets, on highways, why? Too many cars from all places, too fast. Okay, it's about the same as why we see congestion on the internet. Too much traffic coming from all kinds of sources, too fast. Okay, and so how do we address congestion in internet? Well, you guys have suggested many ways, right? So all those cars experiencing congestions can tell the sender, okay, hey, take another way or slow down or whatever, or give up, or write letters to complain to the mayor. Okay, things like that. Yeah, that actually set a stage for the next segment of lecture, the approaches of addressing congestion control. Okay, so let's hear out the first approach, and we'll leave the second approach for tomorrow.
With the scenarios elaborated, you see, particularly in scenario 3, the only solution or the only effective solution to a congestion is to what? Just slow down. And therefore, the two key design elements in a congestion control mechanisms are these. First, detecting when a congestion is occurring. Second, notifying the traffic sources that's causing the congestion to slow down. And there are two major approaches allowing us to achieve those. First is called the end-to-end based approach, the other, the network-assisted approach. Now, from the name of it, you probably guessed. Yeah, end-to-end meant the end systems are doing much of the work, detecting congestion, informing the traffic source to slow down. Network-assisted, on the other hand, is asking the routers to do all this work instead. Let's first focus on the end-to-end approach. So in this approach, the end systems will need to infer if there's a congestion occurring inside the network. If you recall back in TCP, okay, what we're doing is sending multiple packets in one flight to the receiver. Receiver sending back. All these packets and ACKs carry the sequence numbers. So receiver can actually detect a gap, okay, in the packets being received, and therefore sends duplicate ACKs instead of new ACKs. So receiving duplicate ACKs is a way of detecting if there's a loss. Or the sender side can simply time out and then retransmit. That's also a signal of detecting there's potentially a congestion inside the network. So that is, observing from the loss occurring, inferring there's a congestion. One can also observe if there's delay changes. Okay, so for example, when we send packet out, let's track the sending time. Okay, let's track also the time when the ACK for the packet comes back. Calculate the difference, you get the round trip time. And if you observe for a long enough time, you might see, oh, the round trip time is increasing. When it goes beyond a certain threshold, then you could say that also, network is running into a slight congestion there. Okay, so overall, general mechanisms, observe packet losses. If there is an increasing trend, observe the delay. If there is an increasing trend, then you're going into this hotter zone where congestion is likely occurring. Now, taking this approach, we do not get explicit feedback from the internet, from the routers inside the internet. And taking the end-to-end approach, we'll have to also guess or infer the right sending rate. Okay, so this is for the source to know exactly what is the right rate to send the data so that we do not overwhelm the network in the meantime, not being too conservative, too slow sending the data out. And this is actually rather hard to do for the end systems. After all, they're actually at the very edge of the network. The congestion could be happening anywhere inside the network along the path. So what the end-to-end approach is doing is this, okay, guessing. By trying a certain rate and observe if there's a loss, okay, if there's a growing delay. If not, then cool. This is actually within the available bandwidth. So maybe let's raise the rate a little bit and see, right, if there's a loss now, if the delay increases now. If not, then hey, we're still safe. Let's, increase it so that we're not too conservative, too slow sending the data out. Now, but if we exceed a certain point, and as a result, we begin to see loss, and we begin to see the delay increasing drastically. Yeah, that is actually not good. That indicates that we are probably exceeding the available bandwidth threshold, and therefore we are sending data too much, too fast into the network. So if we are detecting these signals of congestions, then that's slowed down. Okay, so end system here to infer, to find out what is the right sending rate is by trying. Okay. Pushing. If we over push it, let's come down again and then try to push it again. Well, if not good enough, slow down again. Right? So this is in fact the approach also taken by TCP. This is actually very natural because TCP being a transport layer protocol, it's actually implemented receiving side, sending side both at the end systems. Therefore, it implements an end-to-end based congestion control mechanism.
Okay, and that's pretty much all for today. But before you go, let me pop this up first. Tomorrow, there's going to be a very interesting quiz coming up. This is actually to give you a rough idea why TCP does congestion control a certain way. And what's special about this quiz, and I want to make sure that you guys know before you go, is because It's a game, okay, we'll be playing. If you pass stage 1, you get 5 points extra credit, okay? And this is for all team members, okay? If you pass stage 2, you get 20 points extra, okay? So if you manage to win stage 1 and enter stage 2, you have already 5 points already. If you win stage 2, okay, you're guaranteed 25 points, okay, in participation for the semester. So this is a big opportunity for those who are not exactly very active, okay, the past few weeks, okay. And if you want to earn some participation points in a major way and quick, this is your opportunity, okay. We'll probably play a couple times, okay. So tomorrow, make sure you attend, and this is a window of opportunity for you to earn the participation grade. And in order to participate in this quiz, you guys will need to use this, okay, the Google Me session there, because in order to do the quiz, in order to do this quiz stage 2, okay, you guys will need to be giving answers interactively while Polly is saying yes or no, or higher or lower, okay. So those who've managed to win stage 1, you guys will be given some time to join a Google Meet session, okay. At least you need to have the audio capability so that you can interact with Polly, okay, to win stage 2. All right, good. So that's all for today, and I'll see you tomorrow morning. Okay, bye y'all. The price will be participation points, okay. But the price of the items, I would translate them to NT dollars, okay. But it's a ballpark price, okay. It's a ballpark price. It can be a little bit higher than usual or lower than usual. But essentially, you can start guessing at some range, okay. But later, you need to be somewhat smart and come up with a strategy. And by the way, the items that you guys will be guessing the price for would be different every year. Okay, so yeah, so see if you can do well. Okay, yeah. Okay, bye.